Hi students, my name is KVR, Chemistry faculty in Sri Chaitanya, Dr. B.S. Rao Nagar campus, Gosala zone. I hope you all are doing well. Today I am going to explain you about periodic trends. It is very important for Neet point of view, and it is also useful to know inorganic part like P block elements easily. Okay. The main periodic properties are atomic radius, ionization enthalpy, it is also known as ionization energy, electron gain enthalpy, also known as electron affinity, and electronegativity. These all are the main periodic properties. Along these, some other properties are also there like electropositivity, valency, metallic and non-metallic nature are also there. But these are the main periodic properties useful in P block elements also. Okay. First of all, I am going to explain about atomic radius. You know about radius? Radius is nothing but distance between center of nucleus to outermost electron in that atom, that is called atomic radius. It is not possible to determine radius exactly. We will determine only internuclear distance or bond length between two adjacent atoms. Bond length or internuclear distance between two adjacent atoms by using X-ray diffraction studies. Okay, it is nothing but bond length. Internuclear distance is nothing but bond length. By using bond length, radius is equal to half of the internuclear distance or half of the bond length. Okay. Atomic radius mainly influenced by nature of bonding as well as number of bonds and also oxidation state. Based on nature of bonding, atomic radius is mainly classified into three types. Mainly three types. First one, metallic or crystal radius. Metallic or crystal radius. Second one, covalent radius. Third one, van der Waals radius. Third one is van der Waals radius. Metallic radius or crystal radius, MR, it is applicable for metal atoms only. In case of metal atoms, metallic radius is considered as atomic radius. Metallic radius is considered as atomic radius. covalent radius is applicable for non-metals. In case of non-metals, atomic radius is nothing but covalent radius. Van der Waals radius is applicable for noble gases. It is mainly applicable for noble gases. In case of noble gases, measured radii or atomic radii is nothing but van der Waals radii. If you apply all three types of radii for the same element, if all three kinds of radii is applied, then order is van der Waals is always greater than metallic radius or crystal radius. Metallic is always greater than covalent radius. It is the order of radii. For same element, if all three kind of radii is applied, the order of radii is van der Waals greater than, metallic greater than, covalent. Okay. For example, if metallic radius of sodium is given as 1.86 angstroms, if metallic radius of sodium is given as 1.86 angstroms, then its atomic radius is dash. Find its atomic radius, and similarly covalent radius. If you observe the order of radii for same element, all three kind of radii is applied. Metallic greater than covalent. Here the magnitude of metallic radii is 1.86. So the covalent radii should be less than 1.86. The value should be less than 1.86 angstroms. Similarly, for metals, atomic radii is nothing but metallic radius. So the atomic radius value is same, 1.86. In case of metals, metallic radius is considered as atomic radius. Okay. One more one based on the types of radii. If atomic radius of a non-metal bromine is 1.14 angstroms, then its covalent radius is dash. Covalent radius is dash. In case of non-metals, atomic radius is nothing but covalent radius. So the answer is same, 1.14 angstroms. Okay, this type of models are given based on the type of radii, very important. And one more, if metallic radius metallic metallic radius of calcium is given as 200 picometers, then covalent radius is dash. Covalent radius is dash. What is the relation between metallic radius and covalent radii? Covalent radii is less compared with metallic radii. So the value should be less than 200 angstroms, less than 200 picometers. This is about the type of radii. Okay, if you observe the trend in group as well as in period, in a group from top to bottom, in groups from top to bottom, atomic radius increases. The reason is differentiating electron enters into new shell, principal quantum number increases. That's why the distance between center of nucleus to outermost electron increases. So in a group from top to bottom, atomic radius increases. Reason is down the group, n value increases. Here upward arrow means increases, n value means principal quantum number, shell number increases. That's why the distance between center of nucleus to outermost electron increases. So radii increases. What about trend in periods? If you observe in periods, in a period from left to right, atomic radii decreases up to halogen. From halogen to noble gas, radii increases, because in halogens the measured radii is covalent radii, and in noble gases the measured radii is van der Waals radii. Van der Waals radii is always 40% greater than covalent radii. So in periods from left to right, atomic size decreases up to halogen, Here principal quantum number remains same. In a period from left to right, principal quantum number value remains same. Differentiating electron enters into same orbit, as well as effective nuclear charge increases. That's why radii decreases. N value remains same. N value remains same. Effective nuclear charge increases. Effective nuclear charge Z effective value increases. That's why radii decreases. Okay. It is the variation of radii in group and period. Now we are going to discuss about ionic radii. It is very important for objective point of view. Ionic radius. Ionic radius. The distance between center of nucleus to outermost electron present in ion. The ion may be either cation or anion. That is called ionic radius. In general, order of radii is anion always greater than neutral atom. Anion always greater than neutral atom, always greater than cation. It is the order of radii, very, very important. Reason for this order is radius is inversely proportional to effective nuclear charge. Inversely proportional to effective nuclear charge. If you observe the effective nuclear charge, in cation, number of electrons are less compared with the number of protons. That's why effective nuclear charge is more, so its radii is less compared with anion. In anion, number of electrons are more compared with protons. That's why effective nuclear charge is less in anion. So anion has large radius compared with cation. Order of radius is like this: anion greater than, neutral atom greater than, cation. It is very important. In NCERT module also some questions are given based on this order. Okay. For example, if you observe the radii of H, H plus and H minus, species with large radii, anion. Anion has large radii. The order is like this: H minus greater than, neutral atom is hydrogen greater than cation. In anion, effective nuclear charge is less, that's why radii is more. One more example. Neutral atom, unipositive ion, dipositive ion and tripositive ion. All are cations. As magnitude of charge, positive charge increases, effective nuclear charge increases. That's why radii decreases. Radii decreases. So order of radii is Fe3 plus has less radii compared with Fe2 plus, less than Fe plus, less than Fe. This order is increasing order of radii. The above order is decreasing order of radii. It is increasing order of radii. It is decreasing order of radii. Higher to lower, from lower to higher. As magnitude of positive charge on ion increases, ionic radii decreases. Similarly, if you observe anions like phosphorus -1, polynegative anion, as magnitude of negative charge on ion increases, radii increases. So the order is like this: P3 minus greater than 2 minus greater than P minus 1 greater than phosphorus. This order is a decreasing order. In case of anions, as negative charge on ion increases, radii also increases. In case of cations, as positive charge on ion increases, radii decreases. Okay, you just remember this one. Anion always larger in radii compared with neutral atom. Neutral atom is always larger in radii compared with cation. Okay. What about isoelectronic series? You know isoelectronic series? Isoelectronic series. Isoelectronic series. Iso means same. Iso means same. A series of atoms or ions having same number of electrons, that is called isoelectronic series. For example, carbide ion, nitride ion, oxide ion, fluoride ion, neon, sodium ion, magnesium ion, aluminium ion, silicon. All ions are mixed along with neutral atom. If you observe the order of radii, here all are isoelectronic because all ions have same number of electrons. If you observe the number of electrons in the above ions, all have same number of electrons, 10 electrons. Okay, 6 plus 4 10, 7 plus 3 10, 8 plus 2 10, 9 plus 1 10. Neon also atomic number 10, 11 minus 1, 12 minus 2, 13 minus 3, 14 minus 4. All have same number of electrons. In isoelectronic series, ion with more negative charge has large radii. So here carbide ion, large radius. Ion with more positive charge, small radius. Small radius or small size. Okay. If you observe the order, carbide ion greater than, nitride ion greater than, oxide ion greater than, fluoride greater than, neon greater than, Na plus greater than, Mg2 plus greater than, Al3 plus and Si plus 4. Okay. It is very important. Now, based on isoelectronic series and ionic radii, what type of bits are important? First of all, if four ions are given and write the correct order of radii, either increasing or decreasing, that is one important model. Another one is like this. If ionic radius of oxide ion O2 minus is given as 1.42 angstroms, then ionic radius of Si plus 4 ion is dash. Find the value. If you observe the order of radii, oxide ion has more radii than Si plus 4. Both are isoelectronic. Both oxide ion and Si plus 4 ions are isoelectronic. They have same number of electrons. In isoelectronic series, negative charge increases, radii increases. So O2 minus value should be always more than Si plus 4. Here O2 minus value given as 1.42. So Si plus 4 value should be less than 1.42 angstroms. Okay. It is one type. Here some ions are given like Na plus, F minus, O2 minus, Mg2 plus. There are 4 ions are given. Arrange the above 4 ions in increasing order of ionic radii. Increasing order of ionic radius. Increasing order means from lower value to higher value. Okay. Among these, ion with more positive charge has less radii. So Mg2 plus has less radii. Mg2 plus less than Na plus, less than F minus, less than O2 minus. Negative charge increases, radius increases. Positive charge increases, radii decreases. It is the increasing order of radii. Okay. This is about atomic radii and types of radii and ionic radii. One more model is there, that is also important. Next one, important model already given in NCERT textbook. Which of the following species will have largest size and smallest size? Here the given species are like this: Mg, Mg2 plus, Al and Al3 plus. Among these, which of the following species will have large size and small size? By applying ionic radii, here first of all observe all are isoelectronic or not. Mg 12 electrons, Mg2 plus 10 electrons, aluminum 13 electrons, Al3 plus 10 electrons. These all are not isoelectronic. Here Mg2 plus and Al3 plus are isoelectronic. Okay. In general, cation is always smaller in size compared with its neutral atom. Okay. Among Mg and Mg2 plus, Mg2 plus has small radii. Among Al and Al3 plus, Al3 plus has small radii. Here, ion with large species with large size magnesium, small size is aluminum ion Al3 plus. magnitude of positive charge more, that's why radii less. Large size is mg, small size is Al3 plus. It is NCERT textbook example, important. Okay, this is about atomic radii, type of atomic radii and ionic radii. Now we are going to discuss about one of the most important periodic property, that is ionization enthalpy or ionization energy. Ionization enthalpy, it is also known as ionization potential or ionization energy. You know the definition? Amount of energy or minimum amount of energy required to remove an electron from neutral gaseous atom like X. The atom is in gaseous state. If some amount of energy is supplied to X, it converts into X plus after losing one electron. For this process, the energy required is called ionization energy. Here one electron is removed, that's why that energy is also known as first ionization energy, IE1. After removing one electron from neutral atom, we will get unipositive ion. Unipositive ion. Okay. In unipositive ion, number of protons are more compared with number of electrons, or number of electrons are less compared with number of protons. That's why effective nuclear charge is more. Effective nuclear charge is more. From unipositive ion, one more electron is removed. One more electron is removed. We will get dipositive ion like this. The energy required for this process is called second ionization energy. If you observe the order of ionization energies for an element, IE2 value is always greater than IE1. IE2 value is always greater than IE1. The reason is effective nuclear charge. Compared with neutral atom, in unipositive ion, effective nuclear charge is more. If effective nuclear charge is more amount of energy is required to remove electron. That's why IE2 value is always greater than IE1. The reason is more effective nuclear charge in unipositive ion compared with neutral atom. Okay. Ionization energy values of elements are influenced by so many factors. The important factors are factors affecting ionization energy values. The important factors are atomic radius. Ionization energy mainly influenced by atomic radius. The relation is ionization energy is always inversely proportional to atomic radius. As atomic radius increases, ionization energy value decreases. If atomic radius increases, nuclear force of attraction over outermost shell decreases. That's why less energy is required to remove electron. One more important factor is effective nuclear charge. Effective nuclear charge. It is very important to solve all objective model type bits. Effective nuclear charge. Ionization energy value is directly proportional to effective nuclear charge. Z effective value. Already you know about in ionic radius. Ionic radius is inversely proportional to Z effective. Okay. If Z effective increases, any radii, either ionic or atomic radii, Z effective increases, radii decreases. If radii decreases, ionization value increases. For example, among Fe2 plus and Fe3 plus ions, ferrous and ferric, which one require more energy to lose one more electron? Among these two cations, effective nuclear charge is more in ferric ion. Z effective is more. Magnitude of positive charge is more. So, ferric ion requires more IP than ferrous ion. Therefore, order of ionization energy is Fe3 plus greater than Fe2 plus. As magnitude of positive charge increases, Z effective value increases, so ionization energy value increases. Next one is screening effect. Screening effect also influence ionization energy values of elements. Ionization energy is inversely proportional to screening effect. Next important factor is penetrating power of orbitals. Ionization energy directly proportional to penetrating power of orbitals. Penetrating power is nothing but attraction towards nucleus. It is more for s orbital compared with p. P has more penetrating power compared with d. D has more penetrating power compared with f. The order is like this: s greater than, p greater than, d greater than f. Ionization energy values are also same. Last one, electronic configuration. Ionization energy values directly proportional to elements with stable electronic configuration. Here stable electronic configuration is nothing but half-filled or completely filled orbitals. Elements having half-filled or completely filled orbitals in their valency shell are more stable. That's why they require more energy to lose electrons. For example, ionization energy value of beryllium is greater than boron. In second period, if you observe second period elements, ionization energy value of beryllium is greater than boron. The reason is the electronic configuration. If you observe the configuration of beryllium, beryllium valency shell contain completely filled s orbital, whereas boron valency shell incompletely filled p orbital. So, completely filled configuration is more stable. That's why it requires more energy to lose electron. That's why ionization energy of beryllium is always greater than boron in second period. Similarly, ionization energy of nitrogen is always greater than oxygen in same period. In second period, ionization energy of nitrogen is always greater than oxygen. It is first ionization energy is nothing but first ionization energy, IE1. IE is nothing but IE1. If you observe the configuration of nitrogen and oxygen, nitrogen has half-filled p sublevel, half-filled p sublevel, half-filled or completely filled orbitals in valency shell are more stable. That's why it requires more energy to lose electron compared with oxygen. So, order of IE1 is nitrogen greater than oxygen. These are the two exceptional cases in second period elements. Two exceptional cases in second period. Similarly, in third period elements also two exceptional cases are there. Magnesium and aluminium, okay. Phosphorus and sulfur. Magnesium and aluminium, phosphorus and sulfur. Magnesium greater than aluminium, phosphorus greater than sulfur. Same reason, stable electronic configuration. Okay, here IP values of elements are mainly influenced by 5 factors. The important factors are effective nuclear charge and stable electronic configuration. If you observe trends of ionization energy in group and period, you already know about atomic size. Atomic size increases from top to bottom. Ionization energy is inversely proportional to atomic size. That's why in any group from top to bottom, ionization energy value decreases. In a period, ionization energy value increases with some variations. Variations are due to stable electronic configuration. If you observe in second period, second period elements. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Here the variations are observed in beryllium and boron, nitrogen and oxygen. While writing IE1 order, lithium less than, boron less than beryllium, or beryllium greater than boron, less than carbon, less than oxygen, oxygen less than nitrogen, fluorine less than neon. Okay. Lithium 1A group, alkali metals. Neon 18th group, noble gases. So in modern periodic table, group of elements with the highest IE1 value 18th group, group of elements with the lowest IE1 value 1A group. For third period elements also we will write like this. Now I am going to discuss about few models related to ionization energies. First one, write the order of ionization energy values of the following. I minus, I plus. Iodine, neutral atom, anion and cation. Write the correct ionization energy value order based on the above factors. The main factor influences ionization energy values is effective nuclear charge, okay, and also atomic radii. If you observe either radii or effective nuclear charge, effective nuclear charge more for Z effective value more for cation, Z effective value less for anion. So the correct order is I plus 1 greater than I greater than I minus. Decreasing order of ionization energy. Okay. Next here I am using the elements like carbon, nitrogen, phosphorus, silicon, second and third period elements. Carbon, nitrogen, phosphorus, silicon. Here 4 elements are given. How to write the correct order of their ionization energies? Very, very important model. First observe the elements present in second, and here carbon and nitrogen are present in second period. Silicon and phosphorus are present in third period. Arrange them into various periods. Carbon, nitrogen, these two are in second period. These two are in second period elements. Okay. Silicon and phosphorus are third period elements. If you write from top to bottom like this. Top to bottom atomic size increases, so ionization energy decreases. Left to right ionization energy value increases with some variations. Here in second period, from moving carbon to nitrogen, ionization energy value increases. So nitrogen has more IP than carbon, okay, in second period. Similarly, in third period, if you observe, phosphorus has more IP than silicon. Among second and third period elements have more ionization energies due to their small size. Therefore, ionization energy order is second period elements have more ionization energies. That's why first highest value for nitrogen, next carbon, after that phosphorus, and least for silicon. It is the correct ionization energy values order of the four elements like carbon, nitrogen, phosphorus, silicon. Second period elements have more IP values than third period. Okay. One more. Neon, Na plus, Mg2 plus, Al3 plus. Correct order of ionization energy values of the above species. First observe, all are isoelectronic or not. If you observe, all are isoelectronic. All have same number of electrons, 10 electrons, 10, 10 and 10. You already know about ionic radii clearly. In isoelectronic species, magnitude of positive charge increases, radii decreases. Here small radii is Al3 plus, that's why it has more ionization energy. It requires more ionization energy. Is directly proportional to either effective nuclear charge or inversely proportional to atomic radius. Apply any one. If you observe effective nuclear charge more for Al3 plus. Similarly, atomic size is less. So, correct order is Al3 plus greater than Mg2 plus greater than Na plus greater than Ne. Important. One more important related ionization energy related model is finding valency of an element. Finding the valency of an element by using successive IP values. Here, for an element X, 4 successive ionization energy values are given. Ionization energy values are given like this. Here IE1 value is 28.6 electron volt per atom. IE1 value. and IE2 value, second ionization energy value is given 74.3 electron volt per atom. IE3 value is given as 946.5 electron volt per atom. IE4 value is given as 1134 electron volt per atom respectively. These are the 4 successive ionization energy values of an element X are given. By using the above 4 values, we will identify the valency of X. Okay. First, observe the value. IE1 value is 28, IE2 value is 74. From 28 to 74, you know the correct order. Order of ionization energy values are always like this. IE1 less than, IE2 is less than, IE3 is less than, IE4, etc. For any element, the order is like this. If you observe the given values clearly, IE1 value is less compared with IE2. IE2 is also less compared with IE3. But from IE2 to IE3, from second to third, there is a sudden rise in ionization energy value. A sudden rise between two successive IP values indicates that the lower one is stable configuration. The lower one is stable configuration. Sudden rise or large difference or large jump or large difference is observed between IE2 and IE3 values. So the lower one means IE2 is stable. Here, how many electrons are there? 2 electrons. These 2 are the number of valency electrons. Number of valency electrons. Number of valency electrons n equal to 2. So, the element X belongs to a group. Element X belongs to a group. X belongs to a group. After finding valency, we will write the formulas of different compounds. After finding valency, group number, number of valency electrons, we will write the formulas of different compounds. For example, write the formula of oxide. Formula of oxide formed by the element. Formed by the given element. Here already you know about the valency of X. X valency is 2. X valency is 2. Oxide ion. You know the symbol of oxide ion? O2 minus. Now, by using crisscross method, we will write the formula of oxide. The oxide formula is XO. The oxide formula is XO. Okay, it is one of the important model regarding ionization energy values. Here, sudden rise or large difference between I2 and I3 is observed. That's why the valency is 2. In some other cases, if sudden rise between I3 and I4 are given, then the valency becomes 3. Valency electrons becomes equal to 3. The element belongs to 3A group or boron family. The element belongs to 2A group are also known as alkaline earth metal. If sudden rise or large difference between IE1 and IE2 values are given, then the element belongs to 1A group or monovalent or univalent. By using successive ionization energy values, we will find the valency of the element. By using that valency, we will write the formulas of different like oxide, phosphate, sulfate, carbonate, like that, by using other anions. Okay, students, this is about ionization energy and atomic radii, types of atomic radii. Ionization energy is mainly influenced by atomic and ionic radii. Both are interrelated, very important. Okay. In our coming class, I am going to discuss about remaining part. Thank you one and all.